that there. Hello. Hopefully there's some people out there watching the live stream, which is always nice for me to know that there's a few of you out there. So welcome if you're out there. This is week 15 of 17. So the fourth project is due, and I will talk about it before we leave tonight. Fourth project is due on December 11th. And then that 17th week, since we don't have a final, what I do with that week is I do one more week of new content. And what I do with it is I take an example from our Go language work and I translate that into the C++ language. And you will do that along with me as a way of introducing you to C++ syntax. And the reason I do that is because some of you, at least, will go on to the next programming class after this one, which is likely to be taught in C++. So I want you to give you a leg up so that you've seen C++ before you leave this class, but also what I'm hoping you'll discover, and we are also doing it in discussion, what I hope you'll discover is that C++ isn't that much different from Go. So moving into a new language from the Go language, a language like C++, for example, is really not nearly as big a deal as some people might think that it is. So that's the 17th week. This week, the 15th week. Next week, the 16th week. We get the last pieces that we need to tackle the fourth project. Now, you already actually know everything that you need to know to do 90 or more than 90% of the project. So I highly recommend that you get started on that project. It's due on December 11th, which is the end of the end of week 16, before we had that last week of the semester. So I'll look at it tonight. But anyway, you already know how to do just about everything that you need for project 4. And then we will add this week and next week a couple of pieces that you will then use, or can use at least, to satisfy a couple of the requirements of the project. So that's where we're at. The discussions were good. So I'm glad that a lot of you are taking the discussion seriously, because I'm going to talk about object-oriented programming tonight, in my way at least. So I am one of those people who thinks that for the most part, the Go language is an object-oriented language. And I would also say it doesn't actually matter if it's categorized as an object-oriented language. You will discover that what we do tonight, as an example, if you look at what we do tonight with structs and what are called methods, that you will find these same approaches being used in C++, which is considered an object-oriented language. So even if people say it's not an object-oriented language, you certainly learn how to do most of the things that you use in object-oriented languages. So take that for what it's worth. You will be prepared to deal with an object-oriented language after this class, because there won't be any dramatically new things for you. You know how to create an instance of a struct, and that is a piece of what object-oriented programming looks like. And then we will add the ability to do what are called methods tonight. And methods is another thing that you kind of see as one of the hallmarks of object-oriented programming. So anyway, I will remind you of that when we're doing it, and you can see in my agenda. In fact, I'm going to edit my agenda, not by taking things out, except for these blank spaces, which I don't like. There's line 16 now. It says common OO pattern, which is object-oriented pattern. So we actually use commonly, at least I do, a pattern in my Go language programming that looks very much like the pattern that I would use in object-oriented C++ programming. So there you go. That part between the bars, we are going to talk about pointers tonight, and it introduces new syntax. But in our programming work, we're going to sort of go as light as possible, as painless as we can when we use pointer syntax. But there's a couple of questions in your homework that ask you to do the reading and take from the reading answers to questions about pointer syntax. So the readings and the homework questions are going to feel a little bit more technical than what we actually end up using in our programming. And that's why the bars are there, is just there's going to be some questions that you're going to need to do the reading to find the answers to, but you won't have to worry tons about the more highly technical things from your reading in your programming this week. Because the programming, hopefully you'll see that the programming is not that scary looking for the pointer syntax that we use. Okay, let's walk through the module before we do anything else. So project 4, which I will have a look at before we leave here tonight, that's due on December 11th. And then there's one more week of class after that, which is finals week for some of your classes if you're taking more than one class, possibly. For us, it's just one more week of learning something new, which has a lab in it and sort of the usual stuff. But you will have your last big project behind you when you get into the last week of the semester. All right, week 15. So we're talking about pointers this week, and programming pointers is weird because the syntax doesn't look like what we describe in our regular language when we talk about pointers. My finger can be used as a pointer in the real world because I can use it to point at things. And we don't really need to dive deep on this, but basically a pointer isn't the thing. Like my finger is not my cup of tea. It's just pointing at my cup of tea. But if someone else looks to me and says, "Where's your cup of tea?" and I point at it, that is a way to get that other person to my cup of tea. So I'm just using my cup of tea. So conceptually, that's all pointers are, is things that point at other things. In code, it doesn't look anything like that, which is off-putting at first. And it takes a lot of practice. And if you go on to the second semester programming course, you will get to use pointers a lot. So we will use the basic pointer syntax in the Go language, and it's very similar to the basic pointer syntax of the C++ language. But we're not going to do anything super crazy with it. It just, you will get exposed to it. You will have code that uses pointers and pointer syntax, and hopefully you can leave with some sense of what it is that we've done when we do the programming work this week. So we got pointers is new, and we got methods that are new. Method is simply a different take on a function. That's all it is. A method, we use that word because we are doing a function setup that's a little bit different than we do a normal function. So for a lot of you, that means, oh goodness, I'm not super comfortable with functions as it is, and now we're going to add something new to functions, and that's true. That's just one of those things that takes a long time for most of us to get comfortable with, is what are functions? How do you call them? How do you pass data to them? How do you deal with the return values? And now we have this new thing. So yeah, just be patient with it like I always ask you to do. Just allow yourself time to feel uncomfortable with it. Work it out in a programming problem like we'll do in lab this week. And over time, you will start to put the pieces together in your head. All right, so readings, of course, as always. Homework as always. The lab, I'll leave this and come back to it in a moment. So what I've been having you do in discussion is kind of enhancing our learning in the class by having you do your own research and then contribute to discussions about some things that aren't directly related to the Go language programming work that we do. So this week is about programming paradigms. Many of you have already encountered this term and have already encountered definitions of what a paradigm is. So yeah, that'll be the discussion, and then hopefully I can touch on it next week after you guys have done your research and had your discussion about it. and then reminder. So homework lab discussion as always, and then individual project 4 is due on December 11th. This next Sunday we come upon is December 4th, so the next Sunday after that, December 11th. Let me look at my agenda. Yeah, okay. So let's spin up a REPL. And set ourselves up to see what a function looks like. So, I mean a method. I'm sorry, a method. So all of this, everything that I have on that agenda really revolves around the use of structs. So we started using struct last week, which is really just what I would call a custom data type. So in Go, to create a struct definition, you use the keyword type, and then you say what you want your struct to be. The thing I can come up with is, for my struct this week is a sport team. No spoilers in chat, but the U.S. played in the World Cup today, so I don't know how that went, but that's probably what got it in my head to use a sport team as my example. Okay, so we have the sport team. I'm going to kind of mirror the way that I set up the lab this week, so you're going to see me capitalize some things that I don't always capitalize. I'm not going to worry tons about that. Anyway, so I'm setting up this sport team struct. I would call this the struct definition. So this isn't an instance of sport team. This is just the definition of what a sport team means in the context of my software. So we'll give the team a name. It'll be a string. We'll give the team a hometown, let's say, which will be a string. Since it's generic, we need to say which sport, which will be a string. And then let's just do something like wins, which will be an integer, losses, which will be an integer. And as a nod to the World Cup, we will have draws, which some sports have. Which honestly I find frustrating, by the way. Go to a game and walk and then leave, and the world is the same as it was before the game started. What happened in the game? Nothing. It was a draw. They might as well have not played. Okay, so anyway, here's, oops, I started to lowercase. The lowercase and uppercase letters, by the way, they do mean something in the Go language. I don't want to get sidetracked too much by this, but in the Go language, things that are capitalized versus things that are not capitalized has to do with if I had a project and I had a whole bunch of Go files, not just main.go, but a whole bunch of Go files. If I wanted to use, say, one of my structs from one file and I wanted to reference that struct in a second file, I would only be able to access capitalized things. This is called access, and some of you have seen that term before as well, which is an object-oriented feature, I would call it. So capitalized things in the Go language are accessible from outside of that file in other files if you had more files comprising your project. Now, we always do just a single file for our whole project. But in bigger software systems, you might have many files in your project. And if you wanted to use things that you had defined in one file in a second file, the only things you'd be allowed to use would be the capitalized things. We would call those the public things. So that's right. So Shamar is asking, so if you had lowercase losses, then that particular piece of information would not be usable in other files. It would be considered private to the file that it was defined in. I mean, I'm simplifying that a little bit, but Shamar, you're exactly right. If I were to lowercase losses, and then try and make a second file in my project and try to access losses, I would get an error saying you're not allowed to access it because it's lowercase. So it's Go's way of kind of limiting or controlling access to information between multiple files in a software system. So capitalized means that it can be accessed everywhere. Lowercase means it can only be accessed within this same file. So if you see me do it in capital letters, it's in part just so that you've seen that, and also probably because it's my habit, because I tend to work in systems that have multiple files associated with them. So for our purposes, it's probably not going to make a huge difference if you go lower or uppercase, capital or not capitalized. So yeah, good point. Good question, Shamar. All right, so here's my sport team. So I'm just going to go straight into how we would often program around this sport team struct. And I'm going to do it in the object-oriented style. So in object-oriented programming, we usually have functions that are designed to work with that struct specifically. So I'm just going to list them out by name here. So we need a function to create a new sport team instance. We need a function probably to alter, or let's say in the plural, one or more of the sport team data fields, functions to retrieve one or more of the sport team data fields, utility functions to perform calculations on sport team data fields, and probably a so hopefully most of this, I'm going to change the terms here in just a second, but if we were doing our software in the object-oriented style, which is what a lot of people do in Go, myself included, when they have structs in the mix. So when we create a struct, we will usually also create several functions to go with that struct that allow us to do things to the data fields in that struct and with the data fields in that struct. So you're going to see this in the lab this week too, and it'll look very similar to what I'm doing here with the sport team. This kind of standard set of functions. So let's start with creating a new sport team instance, and then we're going to have to refactor it over time, but this is a very common pattern in Go programming. So we make a function. Often it will be called new, and then the name of the thing you want to make a new one of. You'll see this in a lot of Go language libraries. So this is a function to create a new sport team, a new instance of sport team. And then in the parentheses, what you'll typically have is a parameter for each field of a sport team. So we'd have a and I'm going to do it this way. So we'd have a name field, and since I have 3 strings, I'm going to group them together. So we have a name field, a hometown field, the sport in question, which are all strings, and then we have a actually probably when we create the sports team, they'll just have all zeros for wins, losses, and draws, right? So creating a new sport team is really a matter of giving it a name, which is the N, a hometown, which is the H, and the sport that they're involved in, which is the S. And then a function like this would return a sport team. And then what we do is we probably just do this, return a sport team, and then we would populate its fields in order going left to right that match it top to bottom. So the first field should be the name. So we will put an N, the N where the name. So this N, whatever it is, becomes the name of that sport team. The hometown goes next, the sport goes next, and then for wins, we'll just start it with 0. Losses, start it with 0. Draws, start it with 0. So that is a very object-oriented style, pattern. That we have a struct, and we have a function that is designed to create instances of that struct. So here's the instance, the sport team, with a specified name, hometown, and sport, and then 0 wins, 0 losses, and 0 draws. The way you would use this function down in main is you would say something like team1 equals new sport team. The name, I'll just go with the, I don't know. We'll go candy style, gumdrops. They come from the town of, you guys are going to get the Chico gumdrops, which I think is not bad. The sport that they play, I don't know. Pickleball, I read an article about that today. And that's it, because the wins, losses, and draws are handled for me. Let's make sure that compiles. Yeah, so it's complaining about the fumped. That's fine. I'll deal with that in a bit. Okay, so that's a very object-oriented way of setting up a struct with a function that is designed to create instances of that struct, so that then in your program, you can create instances like team1, which is an instance of a sport team, using the function new sport team, which takes all your data, loads up a sport team with it, and then gives it back to you. So now I have team1 and it is ready to go. Let's do the toString function, and then hopefully not get you too confused about this. But let's do toString as a method. So that you can see what that looks like right off the bat. So a method is different. And now you can see in my agenda, there's some terminology in there. So Golang methods, that's what we're about to do, as compared to a regular function. So you're just about to see exactly what that looks like. So what makes a method a method? So a method looks like this. That is a method. Now there's something weird going on here because we have never done this before. So what makes this a method is this thing right here. This S sport team in parentheses. Let me make sure I don't lose view of chat. This is a method. It's this thing right here that makes it a method. If I took that off, it would be a function. If I put that in, it's a method. So what does this mean that it is a method? A method is like a function, starts with the keyword func, has a name of the function, it has a parameter list, which is potentially empty, and it has possibly a return type, which could also be empty. The thing that makes a method different is this piece right here, which is called a receiver. So this is something to get used to, but what makes a method is it is a function basically with a receiver. So this function toString must be associated with a sport team as its receiver. So Shamar asks, is the S the sport from the return? So no, this S is actually the sport team that is receiving the function request, is the way I think of it. You'll see this here when I call this method, because calling a method is different from calling a function a little bit. So the way it would look is like this. This is how I would call the method to string. So this sport team here says if you are to use this method, you have to attach a sport team as a receiver to it. So it's confusing at first, and there's a lot of terminology here, but when you so you will see that S, when you have any method, is the setup for a string. No, so this S right here is the sport team in question. So this S is a stand-in for whichever sport team is receiving the method call. So in this case, team 1 is receiving the method call, but I can make a team 2. I need another candy that would be a good sport team name. The gumdrops, I don't need enough candy. Lollipops. Thank you. Good one, Kevin K. Lollipops. Is it okay if they're from Oroville? And, oh, good one. Shamar said lollipops too, with an I or a Y. I'm going Y, although really the Oroville. Does it look better with Oroville being a. Then maybe they'll compete in a different sport. What's that ice one in the Olympics where they slide the thing around? Okay, roller derby. That's cool. Curling. Yes, curling. Roller derby I'll hold on to, and we'll use that for another one. So thank you very much, NK. Yeah, we'll use curling, and then I'll hold on to roller derby for the next one. Okay, so here's what it would look like for team 2 to be the receiver of that method call. So here's team 1 is the receiver of the method call. Here's team 2. So the S is serving as a stand-in for whichever instance is the receiver of the method call. And then we can use the S, and it doesn't matter which instance it is, the S will be a stand-in for that specific instance. And what I want to do here is return a formatted string. So I'll use sprintf because I want to spit out the whole string and not just print it here. So we'll say Chico gumdrops of the Sport League. And we'll worry about the wins, draws, and losses here in just a bit. So here's where and I'm glad Shamar's asking these questions, because here's where the receiver S as a stand-in comes into play. So I can use this S in reference to reference the hometown of the team. So it'll be Chico space name, and then the last one will be the sport. So the S here is serving as a stand-in for the specific team who is the receiver of the method call. So when it's team 1 dot to string, the S will be team 1. When it's team 2 dot to string, the S will be team 2. Kind of like a little bit of magic, because Go will do the work of actually plugging those things in for us. Let's actually print them. So we'll do the printf down here, and we'll just print the string, a couple of new lines, which is produced by that method. And then I'll do the same for the other one. And we'll use team 2. So this is a very new look. Oh, Kevin K. I got some good ones. So Shamar got shuffleboard, Kevin K got curling, and K got curling. So good stuff. And I can come back to shuffleboard and curling as I keep going. Okay, so this is tough because we have this receiver, and where does that fit in when I call the method? Right here. So the method call is receiver dot method name. And then when you define a method, you put a stand-in for the receiver, which is S, and what kind of thing it has to be, which is a sport team, to receive this method call. And then you use the S to access the data fields of whatever instance it's standing in for. So when you're doing the method itself, you're kind of blind. You don't know which instance this is. All you can do is say, well, whatever instance it is, I just am going to refer to it as S in my method. But down here, we actually call the method with a specific object or instance as a receiver. So this is also a very object-oriented look. Let's see if it works. Too many arguments in call to sport team. Oops, I didn't need to put the zeros there. The new sport team already does the zeros for me. All right, so there's Chico Gumdrops of the Pickleball League and Oroville Lollipops of the Curling League. Awesome. Okay, so method. How do we get comfortable with this? I would say for the most part, the way you get comfortable with this is that you read and write enough of them that you begin to recognize what they look like. So you begin to recognize, in the Go language at least, when you have an instance of a struct followed by a dot, followed by a thing like to string, oh, this is a method call, which is a special kind of function that has a receiver associated with it, the receiver being team one. So receiver dot method name is how you call it. How you create one of these methods, you still use func, but then you have to insert a placeholder name for the receiver and the type that the receiver has to be. So the receiver for this method has to be a sport team, and I will use S as sort of a stand-in for the specific instance. So there is a method. So now let's just keep going with the object-oriented style, and we're about to get a shift in the syntax here in just a moment. No, so Shamar, no, the questions are great, so please ask away. So you're not slowing anything down at all. Ask away, because I promise you almost everybody else has the exact same question, but or don't have as much courage to ask. So Shamar's asking, the S here, is that generic? So no, the S is that's the common style in the Go language. I could have called it a sport team and then use that as a stand-in for it. So that S is really just it's the Go language style for a placeholder, like a parameter, is to use the same letter as the first letter of the thing, of the kind of thing it is. So it's a sport team S, but technically that S can be anything that you want. It could be bubblegum, which I can't type, bubblegum. It could be bubblegum sport team if you want it to be, and then you'd use bubblegum as this sort of stand-in for the receiver. So I don't know if that's helping, but the reason why it's an S is because the common style in the Go language is to use one letter for this stand-in here and have that one letter be the same as the first letter of the kind of thing that it is. So hopefully that makes sense. So Kevin K in chat, by the way, agreed that it was a good question to ask, why is that an S? And is that kind of a built-in thing, or how did that get that way? So it's an excellent question. And that S is there. It can be anything that's a legal name in the Go language, but the common practice in Go is to make that receiver placeholder be the same letter as what the kind of thing it is. So if it's a sports team, it starts with an S. If it were a restaurant, then it would be an R, like R, little r space restaurant, if we were writing a method for a restaurant struct. So NK, that's a good one. So NK says in chat, so if our receiver were a car, like capital C-A-R, then the placeholder for the receiver would be a C. And that's exactly right. That is the kind of the common and pretty much standard practice for Go programmers is to do that. So if the receiver were a car, then the placeholder name would be a C for car. Perfect. Okay, so now let's add some of the other functions. We're kind of building up a little sport team code library here. We have the struct that defines what all the data fields are. We have a function. Notice, by the way, that the function remained a function. There is no receiver, so it's still just a plain old function. The reason why it doesn't have a receiver is because you can't have a sport team as a receiver before the sport team exists. And because this function brings the sports team into existence, it must be a function, because you can't have a receiver that's a sport team before the sport team even exists. So this thing brings them into existence, and then from there on out, we can do methods with receivers. Okay, so anyway, what we're going to end up here, though, is with a sport team kind of code library with the struct, and then a function to create instances, and then a whole bunch of, it turns out we're going to write them as methods to work with sports teams. So they're all, the rest of them are going to be methods. So let's do a oh, we actually, no, let's not, we don't need any of that. Let's cut those out. We don't need those because we can just get the data fields directly. Let's work on utility methods. Okay, so yeah, we can very much simplify and get rid of some of those methods. Let's just do utility methods. Although, no, I take that back. So these are kind of optional. I want you to see the whole package. So if we were doing Go language programming kind of using the object-oriented style, we'd define a struct, we'd define a function that creates instances, and then we would define some number of methods that do different operations on individual sports teams. So let's do a method here for sports teams. So we will do it will have a receiver, so it's a sport team, and the common practice is to use an S. And that was great that we had that discussion, because that will help people understand why did he use an N for name? Well, because name, and why an H for hometown, because hometown, and S for sport, because sport. And so we kind of use, where we find opportunities to do that, a single letter. So S for sport team is what people commonly do in Go. So let's do a set name, and then we'll have an N, which will be a string. And something weird's going to happen here in a moment, where we're going to have to change the syntax. But this is a common object-oriented practice, actually, where we have functions that are provided for the purpose of altering the fields. Now, there's no reason why people can't alter the fields directly. They could just say team1.name equals, but this is a common object-oriented approach, so we're going to practice with it. So NK says about shorthanding the struct variables. So I'm shorthanding the values are going to get plugged into the struct fields. That's true. And that's also very common Go language practice. So I don't do it. So what we're talking about, everybody, is this NHS, why I shorthanded that. So yeah, I'm starting to introduce that because that's the common Go language style, um, where it doesn't confuse people at least. So most people would see this NH and S and look at a sport team and realize, oh, that has to be name, hometown, and sport. And that would be the common style, is just to use single letters for the plug-in values there. Save space. It's believed that people don't get confused by that. Now, if I did something weird like this, X, L, Q, then that wouldn't be a good idea, because how are people going to kind of associate what with what? But the NHS, people can look at the struct and write, okay, I'm betting that name is N is name, H is hometown, S is sport. So yeah, I am starting to introduce these sort of common styles that you see in the real world among Go language programmers. A little bit. Okay, so here is a method, has a receiver, takes a parameter, which is N, which is going to be for the name. I did the same thing here. And what I'm going to do is I'm going to say the stand-in S dot name, that's the field, equals this N. Now I don't have to do it this way. I could just let the person down here say team1 dot name equals I don't know another candy. Got lollipops. Oh, Jolly Ranchers. That's a candy. So I could have them just set the name for themselves, but it is common among object-oriented programmers instead to make methods to do this work. This is just something that object-oriented programmers would be familiar with and comfortable with. So we're just going to do it in this style. Yeah, and NK says it's shorter and looks cleaner, and it also gives us some power, by the way. So we could say, for example, here, if we use a method, then we can actually filter off names we don't like. So we could say if n, so let's say that we won't allow gumballs. So one advantage of a method is that we can actually use logic in the method to filter off certain kinds of information. What this logic means is you can't name your team Gumballs. You just can't. You're not allowed. So as long as the name that you are asking to use is not Gumballs, then I will go ahead and allow you to use it. So you can do things like that. Anyway, I'll go ahead and leave that, and we'll experiment with it. So this is the common object-oriented style, and I'm introducing you to that in part because a lot of us use it and a lot of us are familiar with it and like it. You'll see it in code a lot, and you will also see it when you move on to other languages that are actually call themselves object-oriented, like Java, Python, PHP, C++, Rust. There's a lot of languages that do this kind of thing. So there's a method. And we call these methods that we use to alter data fields setters. Is a common term for that. And often they will be named with the word set in them. So set name is how you set the name. It's a setter. And we could do that for the other fields as well if we wanted to. Why not? Let's do a whole library. I'll just do it. So we will have a set hometown H, and I'll scrub off the, I'll get rid of the filtering code this time. And there I'm using that shorthand again, so H for hometown. But before I get too far, we're going to have to do a shift in our syntax. So let's move them up to Reading. That more sounds like a rancher. Sounds more like a, I don't know, like an Alturas or something. Um, okay, so something weird's about to happen. And we're going to have a shift in our syntax. But I wanted you to sort of at least start to get accustomed to what this method thing is, what it looks like when you create a method, what it looks like when you call a method. And it is very object-oriented in its styling. So when you're sort of that discussion when you're talking about object-oriented programming, some people would say Go isn't object-oriented because it doesn't have inheritance. But it does kind of have all the other things that you think of when you think of object-oriented programming. Composite types, structs, in other words, methods, that kind of stuff. Okay, so now let's see the disappointing thing. And then let's go learn the new syntax to fix the disappointing thing. Okay, so you'll notice that Team 1 remained in Chico named the Gumdrops, even though I had attempted to change their name and their hometown. So the problem is, we'll just focus on name for a moment. The problem is what actually happens on a method, at least by default, is the original sport team is not altered. A copy of it is altered. This is common in programming languages that parameters and receivers copies are made for the purpose of the function. So our toString function, as an example, a copy of the sport team is made, which is fine because a copy of the sport team still has all of the same data as the original sport team. But when we try to set the name and we set the hometown, a copy of the sport team is the one getting its name changed and not the original, which is why when we print out what should have been the Alturas Jolly Ranchers, it was a copy of the original, so the alterations are to a copy and not to the original. So how do we make it operate on the original? And that's where pointers come in. It's very subtle looking in code, but we're going to try to eliminate some of the subtleties by being explicit. But let's just do what is required to fix this, just to see how it works. So the way to make this sport team not be a copy of the original team, but the actual original team, is simply to put a star in here. That is it. But it changes entirely what happens. It changes entirely what happens. So with that star in there, we now don't have a copy of the sport team. We have a pointer back to the original sport team. So the Go language understands this to mean, oh, don't generate a copy, but actually just refer back to the original and make alterations to it. So this is a pointer, and it sometimes feels pretty subtle in the Go language. It's just that little star there changes everything. So let me run it again, and that is on the team name, and see what happens to the Chico Gumdrops. So now they are the Chico Jolly Ranchers, and that's because when the name was being changed, we put that star in there, which turned the copy into a pointer to the original. How did I word that in the agenda? Yeah, so a copy receiver versus a pointer or in-place receiver is the way I like to think of it, although I don't need that extra slash there. So a pointer receiver will alter the original as opposed to making a copy. So since I got some people in chat who are feeling good tonight, can someone tell me how to fix set hometown so that it is a pointer to the original and not a copy that gets the new hometown name? You put a star in there. That's exactly right. You put a star in there. And now you are working on the original. Perfect. So Shamar had a star, Kevin K, star before sport team, and now you are working on a pointer to the original, which means that the original gets the alteration and not the copy. Now they're the Alturas Jolly Ranchers at the Pickleball League. That's actually far and away the most important thing for us about pointers, is that they eliminate the copy and allow you to work on the original, which is what you want when you are altering data fields. So I'm going to go ahead and implement the rest of them real quick. Set sport. Making sure that this has a pointer in it because it is going to do alterations. And the sport will be... so Shamar asked in chat, does this kind of help reduce the messiness or the complexity of the code? And I would argue yes. That's one advantage here, is that I think it does simplify the code a little bit, to not be working on copies. But in technical terms, copies consume computer resources. So a copy of a sport team actually consumes computer RAM, which doesn't seem like that big a deal anymore. But if you make copies of a lot of things frequently, and the things have a lot of data in them, you can start to actually consume more RAM on your computer than you'd like to do. So there's actually a memory or RAM savings in using a pointer as opposed to spawning off a copy. Which I'm glad you asked that, Shamar, because we're going to go ahead and use this idea in other places. Okay, so there's set sport. Sport equals S. There's the S. Uh-oh. Got a problem here. I've already used the S for the receiver, so I can't use the S for the sport, so I'm just going to have to say sport. The more I look at that word, the more it looks weird. Sport. Anyway, the S was already being used for the receiver name, so I had to change the parameter name to something that wasn't S. I could. Yeah, so you could. That would be okay, too, to use SP. Is good. So I'll go ahead and do that, NK, because that's a good idea. Okay, so there's set sport. Now, when it comes to wins, losses, and draws, I do want to make alterations to the original. But I'm going to say add a win. So I think what I'm going to do for wins, losses, and draws is I'm simply going to say add a win, and then I will say s dot wins equals one more than what it used to be. So every time they win, I'll call add win. They will get one more win in their wins column. I'll do the same thing for losses and draws. And then I'll also do one for draws. Add draw. So I'm just manipulating an integer counter with those methods. Still using the star because I do, when I call those, want to alter the original. So those are called setters. And it's probably obvious at this point, since I've written several of them. In the Go language, setters need to have that pointer syntax or they won't actually alter the original instance, which is what you want with a setter. You don't always make a setter for every data field, but in this case, I did. Sometimes you don't need to go back and change things later. So you wouldn't need a setter, but in this case, I do want the ability to tack on a win or a loss or a draw whenever that happens in their sporting world. Change the sport, change the hometown, change the name. Anyway, those are what we commonly in object-oriented programming call setter methods, because they set the values of things. Okay, so we got all these star thing. So let's go ahead and close the loop on this pointer syntax. So what you will see a lot of people do um, when they are building these libraries around structs. So you have the struct, you have a function that creates an instance, and then you have some setters. We are going to create some getters here in just a bit. Nah, let's not worry about that just now. I'll leave it. Maybe I'll come back to it. Have some utility methods which we will implement. But what you'll see some people do is they'll go ahead and just make everything be a pointer. Even if a pointer is not required. So a pointer is only required when you need to alter one of the data fields. In the case of this toString method, I'm not altering data, so I don't technically need a pointer. But it is the most efficient way to use the computer's resources is to, instead of spawning copies constantly, just use pointers, which which then don't require copies to be made. So it doesn't change. So notice I made the toString have a pointer, even though I don't actually have to have it, but it doesn't alter the behavior of the method. So, but it does save me a little bit of computer RAM, so why not? But that said, let's go ahead and show you the rest of the pointer syntax. So what a lot of people will do is they will actually kind of pointerify everything. So I'm actually going to have the new sport team return a pointer. So this you couldn't see, but Go was kind of doing automatic two-pointer conversions down below. But what we're about to do is we're going to just kind of make everything be a pointer, make all the method receivers be pointers. And that's in part to get you accustomed to the syntax, but also this is, as far as I can tell, pretty common for Go programmers to do because not making copies of things is more efficient than making copies of things. And pointers are not making copies. So we're actually going to go just pointers all the way through. Everything will be a pointer. So this function is actually going to return a pointer, and that brings us to our last bit of syntax is how do I make a pointer out of something that isn't a pointer? It turns out that this is not a pointer. It is just a sport team. How do I make a pointer out of it so that the function returns a pointer? And it is like this. So that is the way that I will turn just a regular old non-pointer struct into a pointer to a struct. So this syntax is weird. That's how you do it. So good. Kevin K. No, but you were good to think, Kevin K., that there was a piece of syntax to go here. So in chat, Kevin K. said, what's the syntax that's about to go there? And it turns out that it's the ampersand. And this is just weird, and it takes some time to get used to. But what we used to have, let's see what happens if I try to compile this, because I'm going to get an error. So cannot use a sport team struct, which is just a sport team, into a pointer of a sport team. So this really just takes some practice. This is the only place that we need this in our lab today and in my example, but we're just going to go pointers everywhere. So our new sport team is going to actually create a pointer. The way it's going to do that is it's going to create a struct and then use this ampersand to pointerify it. So that turns that sport team into a pointer to a sport team. Pretty weird. Now, technically, I don't think we have to change anything else. Yeah, that's the only thing we have to change, but we're just going to go when we are... yeah, that's funny. So Shamar says, when in doubt, the ampersand. Yeah, these pointer things, if you go into the second semester programming class, you're going to get a bunch of these pointer things. And C++ has the same thing. So it has pointers to things, and it also uses the ampersand to sort of convert something that's not a pointer into being a pointer. And Go is actually in some ways harder because Go sometimes will automatically pointerify for you, but we're going to manually pointerify all of our things. So our new sport team, we're going to make a pointer of it right from the start, which means that we're going to take our struct and pointerify it, which is a me term. That's not a real programmer term. But really, once we've done that, we'll just kind of use pointers everywhere with our struct methods, and we won't ever have anything to worry about for it. So pointers all the way down, all the way from the function to create a new one, all the way through all the receivers will be pointers. So, and it works. Now we've moved the team from Chico to the Jolly Ranchers. We could also, if we want to, well, let's just say the franchise was purchased. Okay, I'm going to skip the retrieving the fields part because we don't need that right now. I am going to add some extra information to this. So, yeah, let's do, I'm going to drop these down to the, so let's put some information in here and we will just say, win percentage is %.1f % to get the percent sign out there. So let's add a win percentage, and we're going to do that through a utility function. So we're actually going to use a function right here, s.get win percentage, and then I'm going to go create this method, get win percentage. So let's do, this will be a utility method that we will create. So it'll be func, it'll have a receiver, and we're going all pointers everywhere now. So sport team get win percentage. And this is going to require a little bit of a calculation. So let's see, we better, I think we better be careful to not divide by 0. So if, so let's first say, games equals s dot wins plus s dot losses, total games we'll call it, plus s dot draws. So we need the total games, right? If total games is 0, oh, we're returning a float 64. If total games is 0, let's avoid doing a divide by 0, which is a naughty thing to do in programming. We'll just return a 0. Else. Okay, so this is going to be a utility method. And by a utility method, what I mean is we're going to perform some kind of a calculation using the pieces of data that the sport team in question carries around with it. So in this case, I want to compute and return a win percentage. So I'm going to total up all the games that they've played, which should be a combination, a sum of the wins, losses, and draws. If I discover that they haven't played any games, then I'm just going to return a 0 because I don't want to do a divide by 0 here. Otherwise, I'm going to return the number of wins divided by the total games. I'm about to get an error, so be on your toes, chat, because we're going to get an error that refers back to something. So this is what I would call a utility method. Has a receiver. It's a pointer because it's just, let's just do pointers everywhere with these methods. So Kevin K has already answered the question. So I can't use wins, which is an int, divided by games, which is an int, to get a float. So Kevin K has already answered the question. To get a float out of here, we need to do a floatify the wins, and that'll give an error too, because we also have to floatify the total games. And you have to do them separately for this to work out right. So we will floatify the wins divided by the total games. We better let's give them some wins and losses. So team1 dot add win. Let's start with 100% win rate, shall we? So let's just give them one win and then see what percent we get back. So 1%. So let's fix that. And this is something to help you with the lab, by the way. Technically, when you do this, it gives you a result between 0 and 1 when you divide like your test score by the total possible. In this case, it's the wins by the total possible. Nice, Kevin K. Multiply by 100. And I'm going to multiply by 100.0 just to make absolutely sure it's all floats everywhere. So yeah, if we wanted to convert it into what most people consider to be kind of a normal percentage, we have to do the division and then multiply by 100 to get something. So 0%, 0%, 0%, that's 100%. Let's give them a loss, which should then be a 50% win rate. We'll give them a draw, which would drop it to 33%. And then we'll also give them one more win, which should raise it back up to 50%. Yeah. Okay, so that seems to be working. That's an example of a utility function, or method, sorry. We could do the same thing to get the loss percentage, the draw percentage. And again, I converted all the receivers to pointers because it's not really hurting anything when I don't need a pointer, but it does hurt things when I do need a pointer. So why not just make all the receivers be pointers? Make the function deal in a pointer and everybody's happy in the end. So I'm going to finish early. I hope I didn't go too fast. Well, I'm not going to finish super early. I got a couple of things to go through. But anyway, so that actually, I think, touches on everything that the lab requires, but let's go have a peek. I will share the link to this REPL with the lecture notes. So I'll just put it there so I don't forget it. Yeah, so let's go look at the lab and see what it has. And then I can also, okay, so there's a request in chat to show line 34 again. For the, hopefully those are correct. Okay, perfect. And I will share the link to this complete REPL in the on the lecture page, so you'll be able to come back and get it. Okay, so anyway, what you've just seen is, in my opinion, a very object-oriented pattern, a composite data type. And what I mean by composite is composed of multiple fields of data. That's very object-oriented. A function that creates instances, very object-oriented. Methods that use instances as receivers, very object-oriented. Setters, very object-oriented. So anyway, that's why I would argue that you can, in fact, learn all of the basics about object-oriented programming in Go, even if some people argue it's not object-oriented. This whole creating an instance and then using it to call methods, that's very object-oriented. Okay, so let's go look at the lab and see if there are any. Let me go back one. It is unit tested, so don't forget it's a unit tested one. But the lab code itself, so it has a movie. I tried to model, I tried to make my example sport team kind of be very similar so that you'd, that's true, Kevin K in chat says that Go kind of has several different programming paradigms kind of borrowed into its syntax. That's true. It has some functional programming components to it. C++ tries to do the same thing as well. I like Go a lot because I think it's cleaned up a lot of the extra mess that C++ has got into it. But that's a personal preference. Anyway, so I have tried to model the example on what was going to be required for the lab. So here's that new thing. Notice it's doing a pointer. So heads up, ampersand coming somewhere in the new movie. Here's a method. There's a pointer, add a like view. So we did add wins, add losses, add draws kind of thing. Add dislike view. So get percentage likes. We just did something like that. Get percentage dislikes. We did something like that. We also did a toString thing. Notice here that there is a template to show you kind of what the format should look like. And then an example, just so you could see if you had data, what the formatting would produce. Yeah, and then you can choose to do or not do anything in main as an experiment, but there is a unit test, so you want to make sure you pass that. So yeah, we touched on everything in our example, and I will share the link to the REPL with you that there is in the lab. So that's cool. Let's go look at the project, and then we will probably finish a couple minutes early today. Project 4. So I call it a vending machine. Some people think of it more as a convenience store. However you want to conceive of Project 4. So I'm switching gears, but we're talking about Project 4 because I want to attach what we've just been talking about into the Project 4 requirements. So I call it a vending machine. You might think of it as a convenience store. Doesn't really matter. It offers a menu of items and lets the shopper choose which item they want. So it is more like a convenience store in that they kind of shop for a while and then they build up a shopping basket and then they say, okay, I'm ready to check out, and then they pay you. But for some reason, I always just think vending machine, even though I know that's not how vending machines work. It's more like a convenience store. Anyway, they buy a bunch of products. You need to be checking to make sure that they haven't sold out. The product hadn't sold out. Don't let people buy things that you don't have any more of. Anyway, so they say, I'm ready to check out. Then you compute a total, and then you make them pay you and make sure that you get all the money that is owed you. So that's what the program does. I like the program because it causes you to exercise most of the things that we've done this semester. So you need if statements. You're going to need at least one loop, probably 2 loops in there. You have to manage data and counters, and you have to perform some calculations using arithmetic. So like all of the do outputs, all of the stuff, kind of all the big stuff is there in this one program. So let's look at the requirements so you can see where some of these things come into play. Documentation, be neat in your source, be neat in your output. Okay, so here, at least one struct. You can use more if you choose, but you need at least one struct and at least 2 methods. So that's what we just talked about is methods. For my money, that little triplet right there, name, price, and quantity, is a great place for a struct to be used to model that data. To model an item in your store or vending machine is a good place to use a struct, although you don't have to. All right, so a struct and at least 2 methods. You can use more if you want. So your store or machine will have a menu of 5 products. You'll let the user pick products, but you need to check and make sure that you haven't sold out. So every time they buy one, you need to count down the quantity that you have in stock and be checking constantly. Are there still any in stock? If there aren't, then just tell them you can't have that, it's sold out. Collect payment, show them their change, etc., etc. So I've also put screenshots so you can kind of see what it might look like. This is the way I did it anyway. So there's my products. Guarantee you I used a struct to represent one of those products and then created 5 instances for water, soda, chips, candy, and apple. And then you can see when I have purchased, I did a number, I selected item 2, which is a soda. I purchased one. The next screen shows that there are now none left in stock. And then I try to buy it again, and I get the message that soda is sold out, so you can't buy ones that are already sold out. And then I immediately go to checkout. So this is the checkout process. You owe me $300. And I just did credits. You can do real money if you want to, meaning like 10.99 and do it as floats. But I just did it as whole number credits because I thought it was more fun to kind of whittle that down into coinage, which I just thought was more fun. I don't think you're required to do that. You aren't. So the way I did it is I kind of had them pay in pennies. And then I thought it was more interesting. We did this program early in the semester, by the way. That's where I got the idea. So they kind of pay in credits or pennies, and then I give them change in coinage. Anyway, so the first time they try to pay, they pay too little. So I tell them, you still owe me 100. And then they pay too much, and then I give them a receipt and their change that I've broken out into coinage, just like we did. Was that project 1? I think I went back and kind of drew on that idea because I thought it was interesting. But you could also do just money. You owe $10.99, pay. I'll pay $5. You still owe $5.99. I'll pay $6. I owe you a penny back. That kind of thing. Okay, so anyway, the pictures are there just as one way you could do it. There is no requirement about how you handle the money. You just have to make them pay and pay enough, and then give them change when change is due. Okay, but that's all there on the project page. So we'll talk about it again next week, and maybe you guys will have questions because next week is the last week before the project's due. So I really enjoyed having several of you guys in chat today. So thank you for that. Made it go good for me. I hope it didn't make me get excited and go too fast. But it's very nice for me to have people in chat to interact with. So thank you for that. I appreciate it. All right, so the link to that REPL will be up on the lecture page, as will the video when I get it processed here in a couple hours. Other than that, I hope you have a great week. I will see you again on Tuesday afternoon next week. Canvas Inbox, Piazza, office hours, all the usual places if you need to reach out for help to me and or your classmates in Piazza or both. All are available as always. So anyway, have a great week. I'll see you on Tuesday next week.